Hello everyone and welcome back to another lecture of machine learning techniques. This is lecture 8 and today we're going to be talking about support vector machines or SVMs. Okay, so far we have seen generative models, such as naive Bayes and so on. And we also looked at few discriminative models like logistic regression, linear regression. So today we are going to learn about another discriminative model called SVM or support vector machine, which cares about where the boundary is between two different types of distributions or two different classes. So what is a support vector machine? The concept is very simple. We have multiple lines that can separate two classes. Let's assume a bunch of data. One is class A, another is class B. They are linearly separable. And we can draw a line through it which is equally far from both the classes. That becomes a decision boundary, which is what the support vector machine effectively tries to do. An example is given here. So we have the blue class, let's take this as A, and we have the red class, let's take this as B. So we can draw three different lines between them, L1, L2, L3. Well, which one would the support vector machine take? Well, ideally, I think in this case it would take L2 because L2 is probably equal in distance to the closest data point of class A and the closest data point of class B. We will look more in this in detail. So, what makes an SVM work? So, we are basically trying to find the decision boundary or the boundary which separates both the classes, which is, or in this case, the margin is the distance between the decision boundary and the closest data points from either classes. So these closest data points are what are called support vectors. And the boundary is called a hyperplane. And the distance between them is called the margin. Since for now we are dealing with 2D, this can be called a line. But if you go to 3D or a higher dimension, it becomes a hyperplane. So let's go into a little bit of the math part of things. How do we find this hyperplane? The equation is basically weight into the data point plus b, mx plus c. It is a line. Since we're in 2D, let's go ahead with that. And the distance of the margin is 2 by the magnitude of the weight, which is basically the distance between two of the closest support vectors of opposing classes. And our goal in SVM is to maximize this 2 by modulo w. So if this line is greater than 0, it is of one class, and if it is lesser than 0, it is of another class. This is how we do this. So far now we have looked at hard margin SVMs. What I have spoken now is called a hard margin SVM, which basically means that we are looking at properly linearly separable data. Now what if the data is not really perfectly separable? What if there's one data point or an outlier that belongs to another class? So for this we have something called a soft margin SVM. It basically allows some slack or some exception. This is moderated by a parameter called the C. The smaller the C, larger the margin and allows more mistakes. But larger the C, it becomes smaller the margin and tries to classify everything correctly. So as C becomes more and more greater, it becomes more into a hard margin SVM. And smaller the C, it becomes more of a soft margin SVM. And this is the major formulas for the soft margin SVM. If you remove this part and only keep half into WTW, it is the formula for the hard margin SVM. And E is basically the slack. This is a very beautiful visualization which talks about the hard margin and the soft margin. just because of a few points, you can notice that the decision boundary would become very small or would be irregular. And in order to fix this, the soft margin SVM will solve this problem. So we've looked only at two different types of data, like two opposing classes. What if there are more? Because you can always have more than two classes, right? So that's why we come into multi-class SVM. A standard SVM is a binary class classifier. Yes, it is true. Which is why when we go to multi-class SVM, we find the SVM between two classes still. Or it can even be one versus many. As we can see here in the slide, we have two common strategies, which is one versus the rest, which is, let's say you train class A and take both of these to be a similar class and train it against, or one versus one, which is you compare red with green and then red with blue, and then draw two separate lines and find whatever is the closest between them or the best performing class within them. This selection can be done based on your data or based on whatever decision that you're trying to go behind. Another problem, we're only assuming linear data for SVM. What if it is non-linear? Look at this image here. We have one class, but it is surrounded by data points of another class. Now SVM wouldn't work here. What do we do to sort this out? Which is why we do something called a kernel trick. Basically what we do is we transform the data points to a higher dimension. And in this higher dimension, it is very much likely that the points are linearly separable. As you can see here, when we apply the kernel function to the data points, these data points get brought up to a higher dimension, because of which now the plane becomes the linearly separable hyperplane. So, how do we select this kernel? Or what is the trick? So basically, kernels have to be symmetric, they have to be non-linear, but it is very, very computationally expensive. Few very common kernel functions are linear kernels, which is basically no transformation or just a normal SVM, or a polynomial kernel, which is used for curved boundaries, or RBF kernel, which is used for Gaussian distributions. For example, this one here is an example of an RBF kernel as it mimics the Gaussian bell curve. So when we come to the math point of things, we basically, this is the formula for linearly separable, where it's just phi xi into phi of xj. But when you use a kernel function, which is k of xi comma xj, the phi xi xj gets transformed to a non-linear form. This is the formula for an RBF equation. So basically, we are converting data points to a higher dimension or a non-linear format in which it becomes linearly separable. Now, we're using this only for classification so far, or support vector classification. What about regression? Well, normal regression tries to minimize every error, but support vector regression only cares about error that falls outside a specific safety zone. So basically, we try to ensure that none of the classes go beyond this safety zone. This is a very easy or understandable visual. We have all the data points, we draw a line through it, and we have our margins, and we try to fit all the data points within this margin, and the points on the margin are again called support vectors. So where do we use SVM? Well, we use it for facial expression recognition, for classification. We can use it for bioinformatics. One of the very common places where we use it is for text categorization. Nowadays, we also are using it for handwriting recognition. But you have to keep in mind SVM is a very, very heavy and computationally expensive machine learning technique. So, a quick summary. What is support vector? They are the critical data points that define the boundary. What is the margin? It is the width which we try to maximize. What is the hard versus soft margin? It is the amount of flexibility we give to the SVM. And the soft margin allows for noise, while the hard margin is very strict in its rule. The C parameter is the trade-off between the hard and soft margin to balance between the margin and the errors or the amount of slack or the amount of exceptions it gives. And SVR is basically SVM but for regression, where we try to fit the data within a tube or within the distribution boundaries. Thank you and see you all in the next lecture.